Take two identical components, like these capacitors, and they will always have a fixed individual ability to store electrical energy, but their actual performance in a system depends entirely on how you arrange them. Wire them end-to-end in a linear chain, creating a series circuit, or wire them side by side in a branched ladder, creating a parallel circuit. These geometric setups use the exact same components, but produce radically different outcomes for total charge and voltage. To figure out what a combination of capacitors can handle, physicists calculate what's called equivalent capacitance. This single value represents the total energy storage capacity of the setup, treating the entire complex network as if it were just one large capacitor. Knowing how to calculate that single number is the only way to design a circuit that hits specific energy targets without exceeding safe voltage limits. Let's look at the series chain first. When you connect a battery, electrical charge travels down a single wire. It hits the left plate of the first capacitor, which then inductively forces an identical reaction on the second capacitor down the line. This diagram shows exactly how that charge distributes. Because the connecting wire between the two capacitors is isolated, its net charge has to remain zero. So whatever charge builds up on the first component pushes the exact same amount of charge onto the second. In a series, the charge, represented by Q, is identical on every single plate. While the charge stays constant, the electrical pressure from the battery gets divided. As the current pushes through the chain, the total potential voltage drops slightly across the first component, and the remainder drops across the second. This algebraic breakdown shows how those divided voltages dictate the math. Since the total voltage equals the individual voltage drops added together, and voltage is defined as charge divided by capacitance, we can substitute those terms. We divide out that constant charge, leaving us with a formula of fractions. For any number of capacitors in a series, the reciprocal of the total equivalent capacitance equals the sum of the reciprocals of each individual component. Because you are adding fractions, the final equivalent capacitance of a series circuit is always lower than the smallest individual capacitor in that chain. You use this arrangement when your circuit must withstand a higher total voltage than any single capacitor could survive on its own. Now let's switch to the parallel layout. Here, the incoming wire splits at a junction, feeding multiple branches at the exact same time. This circuit diagram shows the result of that direct connection. Because each branch runs straight back to the battery's terminals, every single capacitor in this ladder feels the exact same potential difference. The voltage is identical across every branch. But because the physical path forks, the electrical charge distributes itself. To find the total charge the entire system is holding, you simply add up the specific charge sitting on each separate capacitor. This algebra shows how that split charge leads to our second rule. Total charge equals the individual charges combined. Since charge equals capacitance times voltage, and the voltage here is a shared constant, we divide the voltage out entirely. We are left with direct addition. So for any number of capacitors wired in parallel, you just add their individual capacitances together to get the total. This means the equivalent capacitance of a parallel circuit will always exceed the largest individual capacitor inside it. Engineers rely on parallel arrangements specifically to maximize a circuit's charge storage capacity, keeping the voltage locked at a safe, constant level. This summary chart maps out the inverse relationship between the two layouts. Series circuits share the voltage and maintain constant charge, resulting in reciprocal math. Parallel circuits share the charge and maintain constant voltage, resulting in simple addition. For mixed circuits, work inside out. Locate the deepest subbranch and calculate its equivalent value. If 3 series capacitors sit on one parallel branch, calculate their fractional equivalent first. Collapse them into one virtual component, turning a complex network into a simple parallel addition problem. Remember the split. Series is for sharing voltage. Parallel is for shared charge. These formulas firmly dictate exactly how much energy a system can hold and manage. Getting the arrangement right means building a circuit that safely dumps exact energy, whether firing a high-intensity studio flash or powering a life-saving defibrillator.